So can you hear me?
Christophe.
And can you hear me? People who are online?
Yes, I can hear you. Can you hear me?
Okay, so there's a okay. I think it's okay, yeah. Okay.
Yes, I can hear you.
Okay, awesome. So today is the second session of our seminar PMCC, so Paris Mathematical Models of Consciousness. So first seminar, like we give some basic introduction to IIT, and there'll be a second session on IIT, so more on the, let's say, all the different frameworks and articles, like different like explicit expression of phi that were given, and try to see how they all relate to each other. But for now, we have the honor to have somebody that's actively also working on consciousness study, and which is Hayato Saigo, that comes from that's from Japan. He comes from the Nagahama Institute of Bioscience and Technology. Sorry for taking time to read it. He's a mathematical physicist, and who's been working on like foundation of quantum field theory, so algebraic foundation and topological foundation. So on a lot on the categorical point of view on these structures, and also on the foundation of consciousness study, and I think with a very very interesting approach that we will present us today. So it's really an honor for us to have you today. So please.
Just one more thing, tell them that if they want to ask questions, they should raise their hand.
If you want to ask question, I'm told that you have to raise your hand. I mean, not in physical, but on the chat.
On the YouTube.
On Zoom. So not on like this alone in your house, but just on Zoom. Okay, thank you very much. So here, try to put it. It will be okay.
Is that okay? The sound effects? No.
Ask, speak and ask.
Can you hear me?
Ask Christophe. Say, Chris, can you hear me?
Chris, can you hear me?
Yes, I can hear you. The sound is perfect.
Go ahead.
No problem. So here.
Yes.
Okay. So I'm Hayato Saigo. Thank you for the introduction, Gregoire. And I'm very grateful for giving me this great opportunity. Yeah, really great. Several years ago, I published a paper on Annals, this institute, and also as many mathematicians, I'm very respectful to the Henri Poincaré himself, and this room, the Maurice Fréchet, one of I admire him. So it's really great. Among the reasons, I'm very honored. I feel very honored to give this kind of great occasion to give ideas, perspectives, and some active discussions about many things. So please keep relaxed, and question is always welcome. Okay, so I think after following the Gregoire's introduction of me, I also give a very short introduction of me by myself. So I myself is the mathematical physicist who is very interested in quantum field theory, especially the foundation of quantum field theory. Maybe many of you are not familiar with quantum field theory, but you will hear you have heard about the quantum theory. And relativity theory. They are the two biggest revolutions of the 20th century. The quantum field theory is, vaguely speaking, to unify these big revolutionary theories into one theories. Of course, historically, there is a very nice application of quantum field, nice development of quantum field theory, not only the relativistic context, but also the non-relativistic case. But very speaking, this is a union of those two things. But maybe you know, but there is no mathematically rigorous quantum field theory, except for the very obvious cases, free field. But to unify these kinds of things, mathematician, or I'm a mathematician, but mathematician tends to think to unify something, what we really do is to generalize it. So to generalize quantum theory and relativity in a very mathematical sense is non-commutative probability. Probability theory, probability, which we'll introduce later. But a bit of explanation will be needed. You know about the classical probability, a bunch of something. So you know, you heard about the random variables, a probability distribution or something. But this is a generalization of this kind of classical probability theory by generalizing the algebra of random variable, maybe non-commutative. You know, the random variable can add, random variables can multiply each other, but the multiplication itself is defined as a pointwise product, so it becomes commutative. But to treat quantum-like probability, we need some non-commutative algebras. So to replace the commutative algebra of random variables to the non-commutative algebras of observable, that is a non-commutative probability. We will introduce mathematical legal formulation of non-commutative probability later. Okay, so what is a vast generalization of relativity theory? There is many answers, I think, but the most of the general answer is category theory, which also be treated later. Vaguely speaking, it is related to the perspectives and the change between perspectives. So relativity theory itself is working on this kind of law between the change of perspective. And the most general formulation of these perspectives and the change between perspective is formulated in terms of functor and natural transformation in category theory. But today we will not go into the technicalities of category theory and using just for the category which is called dagger category and related things. But do not worry about that. But this is just for some kind of generalization of space-time or something. So to unify these things is for a long time my one of the big issues for me. So now I think I discovered how to unify these things. This is the category algebras and the states on categories. So I published a paper in 2021. And today's talk is treats some perspectives from these papers. And also, subsequently, I published this application of these notions as a foundation kind of field theory, quantum fields as category algebras. If you are interested, please consult these papers. We do not go into details in this talk, but it is also available in archive, so you can consult. Unfortunately, there is some errors. Errors means typos, grammatical errors, and very small mathematical errors. But you can, fortunately, it can be corrected. And I will reflect in the archive. But anyway, you can read these kind of things. So this is the main reference of this talk. And additionally, we give some references. I will explain why I do that. Actually, originally I want to make the foundation of quantum field theory, but interestingly, this combination of category theory and the non-commutative probability is also related to the consciousness studies. So together with Nao Tsuchiya, my collaborator, and Shigeru Taguchi and other collaborators, I wrote some papers to use category theory, a basic, very elementary category theory to formulate, for example, IIT or something, but so consciousness studies to characterize Fourier structure of Fouriers. Structure is means that Fourier is not just a discrete collection of something, but the relationship between them is the most important thing. So from this perspective, we wrote some papers to use category theory into the study of consciousness and cognitions or something. Okay.
More about cost. What do you want to get from the category theory is in the study of consciousness? You said it's like a bit like IIT, so is it like
IIT? Yeah.
Is it like causality or? Is it like
yes, it's a causality. One idea is the causality. Yes, and also in cognitive context, I think some image and meanings as image as objects, and meanings in terms of arrows between them. By using the notion of co-slice or slice category with Miho Fuyama, one of my collaborators, and Tatsuji Takahashi also. So you can think of the importance of category theory, but I think that for you it is most enlightening why category is important. But for example, what is category? Category is a system of arrows and objects. Objects is this kind of thing, like directed graph in the directed graph, but this is like thing is called objects. These are objects. And this is called arrows. So category is something like a directed graph, but having the composition structure. Composition means if it gives F and G, then we can compose them. And this composition should be or should satisfy the associativity. And also for each object, there is, if this is X, there is an unique arrow called the identity arrow of X, which do nothing, like or and for any F and G of such kind. This is the definition of category. So there is many kind of categories in the world. So one of the example is if you consider this as some kind of perspectives in some case, and the change of perspectives becomes arrows. So the total possible change of perspectives is related to, it can be characterized into the notion of categories. So actually, more technically speaking, for example, an example is if you are familiar with group representation, maybe Gregor is familiar. So group representation, then each representation is correspond to the objects. And the intertwiner between the representation is called arrows or something. Many kind of examples here, but I omit here. So what is this for the cognitive or consciousness things? This is called the quantum cognition. In cognitive science, there is many interesting examples which can be modeled by quantum mechanical-like mathematics. For example, one of the famous example is Clinton-Gore experiments. That means if you Clinton and Gore, maybe you remember, but many years ago, there is an election of the candidate of USA presidents. The Clinton and Gore is the two candidates, you know, and there is an enquete about that is Clinton is reliable or is Gore is reliable. The change of the order of questions makes the great change of probability distribution. So of course you can explain this by the ad hoc explanation, but the beauty of quantum cognition is to treat these each which seems to be just a singular, that's a random kind of thing as a systematic mathematical model. Not using classical probability, but using the quantum probability. So they use, for example, the Hilbert space or something, projective measurement model, which is universally appeared in quantum mechanics, but don't confuse that these quantum cognition studies with the so-called quantum brain theories or some like Penrose or collaborators do. Of course, maybe it's important, but I don't know. There is no. I don't know there is some relation or not. I don't depend on these kind of the microscopic level of hidden mechanism. It is just related to the mathematical structure of quantum field. Quantum mechanics. So what is the mathematical structure of the quantum theory? This is non-commutative probability. Okay, so maybe, okay. So this, if you are interested in quantum cognition, you can construct this book, Jerome Busemeyer and Peter Brusas, the quantum models of cognition and decision. There is very interesting examples and the models. So you can consult this. And I think the new books will be, the new revision or something will be appeared, maybe. But another important difference is this. In usual conventional quantum cognition studies, the measurement, maybe you've heard about the measurement programs in quantum mechanics, and but there is the very mathematical legal theory of measurements. So there is, in a sense, so-called measurement problem is not there. It's mathematically very rigorous theories, and in these rigorous theories, the measurement is not restricted to the ideal one, which is called projective measurement. Projective measurement is something like the making the definite value for the ambiguous state to the definite values. But there is a more soft kind of measurements also. So more realistic kind of measurement theory is developed by this guy, Masanao Ozawa, who is also familiar with Ozawa's inequality, which is the modification of the modification of Heisenberg inequality, uncertainty relation. You know, Heisenberg's uncertainty relation is not valid universally, but Ozawa's inequality is valid universal. So this guy makes a general theory of measurements, and by using the notion of quantum instruments, which is a generalization of projective measurement, vast generalization of quantum measurements, and he and his collaborator, who is also the originator of one of the originators of quantum cognition, Andrei Frenkov, wrote a paper that the application of quantum instruments to solve seemingly difficult problems of quantum cognition, which is related to the question order effect, which is the Clinton-Gore kind of thing. And also the response replicability, it means asking A, asking B, then again A kind of sequence is not modeled only using this projective measurement under the condition of the quantum order effect, question order effect, and they do this kind of solve the paradoxes by using the quantum instruments. So summing up, there is many important example is cognitive science, which can be modeled in quantum mechanics. But why? This is my issues of my talk. From the pragmatic point of view, this is not a real problem. You can use anything, of course, but from the also some kind of metaphysical or philosophical point of view, of course, you can ask why quantum mechanical mathematics is useful to model cognitive sciences or consciousness study. Actually, not only cognitive, but more Queria-oriented studies is now we have submitted a quantum Queria hypothesis from quantum cognition to quantum perception. Quantum cognition conventional studies is related, for example, the decision making or something. So some kind of measure related to this kind of definite value, making definite value kind of thing. But reflecting our Queria here, you feel this, but not by the definite value, I think. There is a vague impressions, vague. Sometimes you can make this very clear, but usually we believe that not every Queria has having a definite value. So I think that this kind of thing also should be a model in this non-commutative probability theory. So I will introduce what the non-commutative probability theory is and what is the relationship of category theory and this. So do you have any question? Okay. So I will erase these things. Okay. So the non-commutative probability. Non-commutative probability is, mathematically speaking, the study of non-commutative probability space. But what is non-commutative probability space? That non-commutative probability space is a pair of two things, which is called observable algebra and state on it. Here, R is considered as a star algebra. So we will introduce the notion of star algebra and taking some example. And also the state is in the quantum case, the complex number is used, but in general, maybe the real numbers is okay, or some other rigs. Rig means something, this is some kind of number system with plus and multiplication. So of course you can think of this as a complex numbers or real numbers or anything you want, or tropical one, max plus, minimum plus kind of thing. But we introduce a notion of star algebra. Star algebra is, first of all, what is algebra? Algebra is a vector space with multiplication. So of course, a complex number itself is one of the example of the vector space over complex numbers, and it has, of course, the multiplication. But there is many things. For example is matrix algebra. Because you know I suppose you know that in the matrix algebra you can add the same type of matrix and also multiply them, and the scalar multiplication, and the system of all the matrix can be considered as a vector space. Okay, so it is actually generalized into the notion of a module, but you can omit this. Probably, okay. So another example, and the star. What is star? Is a generalization of the complex conjugate. Generalization of the complex conjugate. That means etc. If this is a complex number, you have the conjugate, complex conjugate here, and of course linear. It is the example in the matrix algebra case, with a complex number, then the star is defined as the transpose and complex conjugate. So this is called L-meet conjugate. So if you know about L-meet conjugate, the star algebra is the vast generalization of matrix algebra with the L-meet conjugation, you know? So every modern quantum mechanical textbooks treats this star algebra. So this is related to the algebra of quantum observables, physical quantities. So what is the state? This is, I think, the most important and impressive point of this talk. So conceptually, this is algebra of quantities. Another example is another very important example is algebra of random variables. Because random variables, you can add random variables, scalar, multiply, multiplication. Okay, so it's commutative. Commutative means AB gives you BA. But in general, in many case, AB is not equal to BA in general. So this is a reason why we call this non-commutative probability space. Generally, if you are started from the commutative star algebra, more technically, commutative C star algebra, you can ignore this technical words, but the commutative, kind of commutative star algebra, then you can recover the random variables over probability space and the probability measures on it by this. So, okay.
But you mean that if take a distribution, L2 functions on for a given distribution, you can see it as a star algebra, or are you saying that the state you can see it as a distribution on the star algebra of the compact function?
Yeah.
Which statement do you mean?
If you choose state. So I had rushed into the but of course you should define state and state a clear statement.
Sorry, can you just rephrase a bit Grégoire's question, because I'm not sure everybody can hear with the microphone. So what was Grégoire asking about?
Grégoire is asking about what is the content of reconstruction from commutative algebra. So actually, in this level, famous Gelfand-Naimark reconstruction from the commutative algebra, star algebra, more rigorously, commutative C star algebra, you can reconstruct the compact house of space, and giving some states, you can reconstruct the probability space on it. Yeah. Okay, so the notion of states. State is considered as a function over this star algebra, satisfying that linear means a usual linear. We omit the multiplication, and positive. Positive means and unitar. Unitar means we suppose that it has a multiplication unit, E. Like in matrix case, it is just identity matrix. So unitar means phi. So multiplicative unit is conserved. So this is called the state. Of course, I think that most of people will think about it. It's too abstract, but it is quite a natural condition, because state is just a generalization of expectation functional. You know, every textbook on statistics point out that the expectation enjoys very beautiful property, that the expectation of random, sum of random variable should be the sum of expectation, you know? Or I omit the scalar multiplicativity, but this is this condition. So phi gives you for each variables into some expectation values, you know? So this is a very natural condition for the state. So state is, conceptually speaking, if you want to do science, quantitative science, you should think of some quantities, and almost all cases you can add and multiply. And then, if even if it is very deterministic, it's okay. But in general, it is statistic. statistical, because every time you want to pull out the output, there is some random nature of the results. Then what you want to is to connect the model and expectation of some random variables. So to do science is just identify this stat algebras under this state. But why stat is needed is here, positivity, to represent the positive. For example, in real case, the squared thing is always positive. Positive means 0 or positive. And in complex cases, complex conjugate should be positive. The x and x complex conjugate should be positive. So in matrix case also. So this positivity corresponds to the generalization of positivity of probability distribution. Because if you have some random variables which is always positive, then expectation should be positive. Why? Because the probability should be positive. So this is a generalization of positivity of probability distribution. The third condition is nothing but the generalization of the total probability should be 1. So if you consider the random variable which takes a value 1 every time, then expectation should be 1 because the total probability should be 1. So all the classical probability, and if you give some probability distribution then, for the compact or the compact space, then you should have these properties. So the state is just a statistical law. So the very beautiful theorem by essentially the Gelfand, Naimark, and the Saigo, who is a mathematical physicist, that if you are given, of course, this is a slightly generated version of GNS, but if you are given the non-commutative probability space, this is star algebra and states, then you can construct a Hilbert space. A Hilbert. Of course, directly it is pre-Hilbert space, but you can make a completion. So I omit this Hilbert space. And phi, which is a unit vector. Unit vector means a Hilbert space is the linear, this Hilbert space is linear space, vector space with inner product. Inner product is very important because the length or angle is meaningful if you are given the inner space. If you are familiar with statistics, the notion of covariance is very important, for example, or the machine learning people also do the make an angle or consider the length of something between data or something. So all depends on the notion of inner products. So the Hilbert space is a very general, natural generalization of usual Euclidean space. It is called the Hilbert space. And the unit vector is length 1 vector. And by this, the expectation of A is represented as this. This means this vector and multiplied by some this A tilde means there is a called a representation that is for each element, this A is represented in the operators in a Hilbert space, and the expectation value is given by this. But this is nothing but in every textbook in quantum mechanics, every undergraduate in quantum mechanics is running is this. So all the wave function or something, many complex thing is the purpose of to calculate is just to calculate some kind of expectation by this formula, Borel kind of formula. But it is no accidents. So you know, star algebra and state. Then you have the Hilbert space or something, the quantum mechanical thing. So why quantum cognition is important is one easy answer is because it is related to quantities and the statistical law. So even in classical case. But so the one answer, the easy answer is this, because it is quantity and the statistical law. But of course, you may think of another question. Why not classical probability? So this means that in any case, in any science, the quantum non-commutative probability space works. But why not classical probability? Classical probability means if this is commutative, then another representation is a degenerate, a kind of degenerate version of this, like classical probability space. It means some sample spaces, some measurable sets, and probability distribution. So usual one. If this is commutative. So the more fundamental question is, why not commutative? From where the non-commutative arises? So the answer is, my answer is, it is because the categorical structure is there. Okay, so, do you have any questions?
Yeah, I mean, I guess you are going to expand on that. When you say it is because of the categorical structure that we need to invoke
non-commutative
from first principle,
yeah,
not just from this experiment using these polls on politicians, but it's deeper.
Deeper. Okay. So I think this is not a mathematical statement, just my kind of metaphysical statement. But okay. Mathematically, if you are given some star algebra and states, then you have the quantum mechanical mathematics. Okay. But the next question is, why star algebra or why non-commutative or something is the more interesting question. The one idea is that if you are given the categorical structure, category, then you have the natural star algebra and the natural notion of states on that. So I think this is why the quantum cognition, the quantum Fourier kind of phenomena appears. So, okay, so let's go into the notion of category. So for as a slogan, quantization as categorification. Maybe you know about the term quantization. You know the quantization.
Maybe you can just restate.
Yeah, quantum physics, the classical physics historically precedes quantum physics. You know, So in the original era of the quantum mechanics, there is a very useful principle that called the correspondence principle. So in classical physics here or their structure, then quantum structure should obey this kind of analogous thing. So from the classical theories to quantum theories, how to make classical into quantum is a main problem to construct a quantum theory. It is vaguely called quantization. But like Heisenberg invented some theory called quantum mechanics and or maybe matrix mechanics. This is called quantization. But from my viewpoint, this can be interpreted as a categorification. So I will explain what it means. And just for the remark, this notion, quantization of the categorification is, of course, very useful word, but from the metaphysical point of view, this is a bad term because quantum precedes classical ontologically, I think, because that means, of course, both are important. But from the epistemological point of view, the classical precedes quantum, I think. But classical nature will emerge from quantum theory. So the quantum quantization is a ontological direction in general, and the categorification is ontological. So it is just some kind of practical name. So the quantization is from commutative to non-commutative. Non-commutative. Then categorification is from set to category. Set, okay. About terminology. Because it sounds like the deformation of the quantum as a deformation of classical, category as a deformation of set. But from my viewpoint, the classical thing is a degeneration of the quantum things, and also the set is a degenerate version of category. So I will explain it. Very simple thing. Set is considered as the special kind of category called discrete category. Why? Because if you think of the set, just mere set, it is as an image, you have this kind of image of sets. So points and this totality. But it is a trivial kind of categories because if you can think of elements as objects, then considering this identity errors. Because actually in category theory, you can identify each object and identity errors because it's naturally one-to-one. So if you can think of the sets as a category consists of only identity errors, in other words, objects. But in general category, and it is called discrete because it is discrete. But in general, category has the links between the two elements. This kind of thing. The classical idea of the scientific study is as follows. Even if you see the very complex phenomena, by changing the perspective, it will be considered as a discrete category. For example, Fourier analysis. Fourier analysis is something like making things discrete. With a continuous thing should be analyzed by frequency. Each frequency should be a kind of discrete one. This is the spirit of Fourier analysis. Actually, in the age of dawn of quantum mechanics, there is called a very interesting phenomenon that discretization of energy levels. So from atoms, you have the very discrete spectrum emitted by from atom. The light has a discrete spectrum, and there is a many interesting law between the relationship between the energy levels. First, they think of how to make these things into physics. They focus on this each level itself and considering the Fourier coefficients, the law of Fourier coefficients, but it fails. Why? Because to describe the law of transition between energy, we need to focus on this instead of this. So this is a discovery by Heisenberg. Alan Kohn, who is a very famous mathematician, who is maybe professor of the College of France, who wrote a very interesting book called titled by Noncommutative Geometry. In the introduction, you can read over the very interesting remark about that. Heisenberg focus on these hidden transition components and preserve the Fourier, the algebraic features of Fourier analysis. What is this feature? It is called convolution. Convolution may be known for the AI people also. This is convolution is something like to evaluate something we can decompose in many ways and sums up. This is a structure of convolution. Like a matrix multiplication, you can think of matrix multiplication times plus. It's what in the matrix multiplication do is something like in the, for example, Markov chain. You can think of Markov chain. Then original states and other states, you can retool here or here or here, and all the probability is summing up. This kind of structure is called convolution. The Heisenberg, so the Fourier analysis is something like the transformation of this complicated convolution into the pointwise product. This is a Fourier analysis. So the Heisenberg do the convolution on these transitions. This is Heisenberg's finding. But of course, it is too abstract. So
since you're talking about a harmonic oscillator, a
Mhm.
dagger A, jump from
Yeah.
and what is it? I don't see the liquid convolution in this case.
It is just yeah, because A is represented by this kind of matrix A star also the dagger. So matrix multiplication is just one example of convolution.
I mean, yes, you can apply convolution by applying, running multiplication.
So but here it's part. So would you? I don't understand.
Mhm.
So can you maybe just like for you're saying that a dot a dagger? You say multi. I don't understand the statement. So what is a convolution in this case? Like if you want,
It is just a matrix multiplication.
Okay, so
Maybe it is
That means that in this case, you convolute by no movement, there's no action. Because
no.
there's no translation, there's no, just you stay at the same point. That's what you're saying.
No. For example, if you think of three things and this transition, so I will explain it later, but this transition can be represented by the three by three matrix. Yeah. And this here I say this convolution is just a matrix multiplication of that.
Think about the image processing. When you want to blur an image with a Gaussian kernel,
Yeah, but no,
convolute two matrices that you do it to convert.
Maybe it's just for the terminology. So just forget about the convolution. It's because we can define the convolution in the very general notion of convolution in very general context just after this. So you can call anything, just multiplication. Yes. Any matrix multiplication can be considered as a convolution in the general setting. So just call it multiplication is okay. So that is.
Any remark or follow-up from now?
Okay, so I think that your question is solved by just defining the notion of this.
Yeah, exactly.
Yeah.
Maybe it's, maybe I don't get the point. Sorry, this is
No. So just, yeah, I think that
Well, I'm going to go into Fourier, because you were talking about Fourier. So if you do your convolution into the Fourier space, it becomes just simple multiplication of the spectra of your time of the space domain.
Because just for me, you can convolve Saigo, you take a matrix, you take a single, you translate it, you make a matrix, and then you just do multiplication with another one.
Okay. Convolution, yeah. So it's just depend on the definition of convolution. Yeah. So usual convolution in Fourier analysis is a more simpler case. This is a more complex case. Complex means it because this convolution is non-commutative. This okay. So the Fourier case is a special case of the general notion of convolution, and he replaced the general.
Are you saying like that? So you're saying that just the so you're looking at the matrix as a
matrix as a function over a category.
Yeah, okay, and then I understand. So that's why if you consider that you have arrows in every node, then
thank you very much for the very the question which clears my statement. But the point is that we have from category.
I'm sorry.
Okay.
I think we should just pause because the battery. The battery is done. I'm just gonna switch batteries really quick on the on the mic.
Okay.
Maybe you can tell that so that we don't have a lot of sound.
So 5 minutes or so, maybe.
No.
Just
a second. I'm just gonna turn that off and we.
It's just below half.
Okay, so
Okay.
Okay, so speak again and ask Christophe if you can hear. Christophe, can you still hear now?
Can you hear me?
Christophe, we changed the battery. Okay, sorry about that. Can you test on your go ahead.
Can you hear me?
Yeah, good. That's good. We can go. Thank you, Christophe. Sorry about that. All right. Please go ahead.
Okay. So what we have in mind in the slogan quantization as categorification is that not necessarily discrete category, the in general category to the algebras. It is in general non-commutative. Here R is ring. Ring means ring without negatives. That's just assuming plus and times. But you can think of the ring with negatives. So just think of some number system. For the quantum mechanical use, it is C, complex number is useful, and the more general cases, C algebras will be, maybe non-commutative is okay, but anyway, we can define from C to algebra RC by defining this. This is a set of functions from C to R, such that here, I think it is more instructive rather than state just by letters, it's better to think by picture. The condition is that for each object C here, there's maybe infinite numbers of arrows is incoming and infinite number of arrows outgoing. But alpha should satisfy this finiteness condition. That is, for each C, there is only finite number of arrows which has non-zero values. So like, this is a number A, B, C, but this is 0, 0, 0, 0, 0 or something. Then here a number A prime, B prime, C prime, these are 0, 0, 0. So for each object, there is only finite numbers of incoming arrows which has non-zero values. This is so for each arrows, you assign the numbers. You know, so the essential intuition is that this alpha is taking each arrows into coefficients. So this becomes a vector space. This RC becomes vector space because you can add the functions as usual and the scalar multiplication is natural. The point is multiplication. How to multiply these functions? So you can define the multiplication as follows. This is nothing but what I call the convolution. That means to define this is to in this RC is to define the each values for each arrows. So for any C, we define the value of the alpha beta on C as this. What is this? This is C can be decomposed into many kind of arrows. For each decomposition, alpha, beta, alpha C times beta C prime, then adding them all. But by finite test conditions, this becomes actually the finite sum. So it is very defined. For even if the C is C has infinitely many objects, infinitely many arrows, it's okay. So you can define this multiplication, and we get this non-commutative algebra. When it is non-commutative, it is a good exercise, but interesting thing is that if there is, even if only one arrows between the different objects, then it is necessarily non-commutative. So the only cases, two extreme cases possible to be this algebra commutative. One is, discrete case. Another is so-called monoid, commutative monoid case. Or more generally, these kind of. So there shouldn't be any links between the two distinct objects to be commutative. So if there is an essential link between them, this must be non-commutative. So the Heisenberg case is the simplest case, and which is corresponds to the infinite matrices. So, but what about star? So then this is a very general, and it is quite beautiful that you can see this is a generalization matrix algebra, because if C is this kind of so-called indiscrete category. Indiscrete means there is only one arrow for each pair of objects. This is called indiscrete case. In general, there is many arrows between two objects. In this case, it is not called indiscrete. But indiscrete case, this is just a matrix algebra. Under this case, commutative algebra case, especially the so-called natural number as a category, that means 0 is an object and 1, 2, 3 numbers are arrows, and composition is addition. Then this is becomes polynomial algebras with one value. So every interesting algebra in high school mathematics is an example for this category algebras. So what about the star, which is important in defining positivity? So star here, how to impose this star structure? Then we need the leak as a starting. It means some kind of conjugacy here, like a complex. And of course, real number also have conjugate, which is very trivial one. And this should be dagger category. So what is dagger category?
Maybe you can write on the board dagger.
Dagger?
Dagger, right on the board.
Okay. This is called dagger.
have a question.
Of course.
RC.
So
this is I read a bit of the article, which was very interesting. Is this like something that was already considered before your article?
A good question. Actually, it is considered before, but very rarely. The one example is Mitchell, who is a categorist, 60s or something, who works on the called embedding theorem of the abelian categories. Abelian categories is an abstractly defined category, which is very good category. You can do homology on that, homology or something. So abelian category is very good category, and the typical example of abelian category is category of abelian groups. But this relation is not trivial. But Mitchell do the works that the abstract abelian category can be embedded into the concrete abelian category, which is the category of abelian groups. So this is very famous guy. But Mitchell defines this under the different name. So in that sense,
For a big one.
no, not really. It's just
the second question is so if you take R equals C and you consider your category to be composed with all the morphisms that you can, but only one. You take every couple of points for directed one is an arrow, then you can get matrices, but you do not get all the operators on the Hilbert space. So if you have an idea of what you get, of course, probably something that is dense, but can you characterize it in terms of regularity of the
very, very important question. For example, even if this is a pair of, natural numbers, a group of natural numbers, it is unknown. Unknown means actually it has the multiplicative unity. Multiplicative unity. So it contains this kind of matrix. So it is not a finite linear combination of finite rank. So it is wider than such kind of finite rank matrices or something. So it is not contained in L2 in general, if the objects are infinite. So it is quite interesting kind of infinite matrices. But you know, if you consider very naive kind of infinite matrices, the product does not, multiplication of products is not associative, or so violate many natural conditions. So people does not want to work on infinite matrix, but go on the L2 space and operators something because it is very defined for such kind of thing. But this approach may be useful. This is some silly. It is very, how to say, interesting object as just for mathematics. It is a very interesting kind of matrix. And my wife pointed out that if you study some category C and you get this is also a rig. So you can consider like RC, C prime kind of thing. So we have some fractal like, so deeper and deeper infinite dimensional matrix algebra. So yeah, it is, I don't know, it is physically important, but I think it's very, at least mathematically interesting kind of thing. So the question, the answer is, it's open. How to define the suitable topologies, how to define some matrix maybe or something is the very interesting open problem. Okay, so then we have the category and category algebras. And also we should point out that usually the term category algebra is used for the more restricted version of this. That just a finite linear combination of arrows or something. But it is wider. I think as far as I know, Mitchell is the first guy, but do not proceed in that directions, I think. Why I want to have this kind of thing is this is becomes multiplicative unit because it is important to define the notion of states, because you remember that the third condition of the notion of state is preserving multiplicative unit. So, of course, there is a method to add the multiplicative unit to the algebra which does not have a multiplicative unit, but it naturally has multiplicative unit. Okay, so just the remaining point is this: how to consider the star structure. Then we should have the notion of dagger categories. In general, category does not have any symmetries. Symmetry means even if we have the arrow from here to here, it does not necessarily have the reverse direction. But the dagger category is a kind of category which has, for any f, we have f dagger, which reverse the direction. So in a sense, dagger category is very symmetric category. So involution structure is equipped. But point is that if is identity, for example, this x, y, if it is holds, f dagger is called inverse of f, which is in the meaning of group theory. But in general dagger category, it does not hold. So assumption is that this dagger should satisfy this changing the composition direction, and the identity should be result. So this is the dagger category, and there is many interesting category that has the dagger structure. I think that many, for example, I have an occasion to talk to this kind of notion to physicists, for example. Some physicists feels very difficult to understand why it does not hold in general. For example, I think they are too familiar with category sets. Set means object are sets and are other functions. Then it is quite difficult to understand this. But the seemingly very much like set category there, which is the object is sets, but arrow is relation. Then this becomes a dagger category, but not hold this. What is relation? So if you consider x, y, relation is, the function is such kind of thing that if you are given one input, then there exists a unique output here. Unique output here, unique output here. This is a notion of map or functions. But the relation is more general thing. That is, it can have the multiple outputs, maybe no outputs. Here, this kind of. This is allowed. This is relation. But in this case, the composition can be also done for like if this and this and this, for example, by connecting just this. Yes. But it is not this case. For example, this. If this is a relation F, the dagger relation is that just taking reverse relation. This is dagger, but it is not inverse. Not why not inverse? The IX is something like this. Only this and this. But considering this and this, we have by the composition, we have, for example, here goes to here, here goes to here, but the composition here. So we have this kind of relationship between them. So it is not the original one. So F dagger is not IX. So interestingly, this category there is very much like another category called HILB. HILB is objects categories, Hilbert space. And the arrows are linear operators, bounded linear operators. Some researchers think about this relationship. This analogy is not accidental. So they consider the common structure of these things, because in REL, you can also make very quantum-like mathematics in REL. So they consider the common structure of these things is very essential for the quantum mechanics. What is this common structure? This is called dagger category. Actually, most of researchers do the dagger monoidal category, but I don't assume this monoidalness. But here we have the dagger category or the notion. I think this dagger category is also considered as, so the point is, classical spacetime consists of points. The quantum spacetime should have considered as a system of arrows. So this categorification is the basis for this here C prime, RC2, RC prime. Here, this is a discrete category, sets. Here, the dagger category. Then we have the commutative algebra. Here, the non-commutative star algebra. So for me, this relationship is replacing the classical spacetime into the more by dagger category is useful for the quantum field theory, but at the same time, you can think of this structure in the consciousness structure. Two things, at least I can say that two things. One is the very low level point remark. Our brain is consisting of course, neurons and the relationship between the neuron activities, like synapse. It is mediated by electromagnetic field. Then if there is an electric current here, then you can think of the reverse direction, of course. So the very micro level, the consciousness will be supported by the dagger categorical structure of the brain activities. But of course, it is also important, but more macro level, of course, the human intelligence, for example. I don't know, there is a trivial relationship between these levels, and it is open, interesting problem, but more phenomenological level. It is known that even in the child, human child can think of the converse relation. Like actually, we discuss on this important reversing the direction in the consciousness in a projective model of consciousness also is related to this kind of change of perspective structure of the dagger categorical structure. Then, if you want to make this qualitative relational structure into the scientific studies, then we should connect this some kind of quantities. Then what is the suitable quantities to characterize this? I think the answer is category algebras. This is observable algebras for this kind of structure. Then the last question is that, what is the states on it? Then of course, this is a star algebra, so you can define the states on this as just as before. But interestingly, this state on RC can be represented into the positive definite function. On C. What is a precise meaning of positive definite function or positive semi-definite function is written in my paper, so please consult that. The point is, this is just the generalization of the positive matrix or something, or the reproducing kernel or something. So this is quite interesting for me that each state can be represented by this thing, which is, intuitionally speaking, which is just taking a weight on these things, having some positivity structure. So intuitionally speaking, this category algebra is something like the polynomial algebra which replaced by letters by arrows and the coefficients here. Then what states do is assigning each arrows into the expectation value. So just for considering some category algebra, you can check from the definition, you can check here, iota means that this iota C means that for arrow C coefficients is 1, the other coefficients are 0. So you can identify this iota C with C itself. Then this is a theorem from the definition. It is very intuitionally clear that if G and F is connected as this, the multiplication is defined as this. If not, like not connected, then the multiplication is 0. So this RC is considered as a polynomial algebra, non-commutative polynomial algebra generated by arrows, and the coefficients are numbers. So this is intuitionally interpreted as a linear combination of the indeterminates as arrows. So then the state on this algebra is nothing but assigning each indeterminates to some excitation values. So the states on this is just some kind of making the weight on these relationships. So my idea is that he has some causal. This is a very vague proposal, causal or some categorical structure related to the related or supporting the consciousness, gives you the some algebras. Each element of this algebra is some kind of a linear combination of the relationship. I propose that this is related to the Curious. And the states on it. Corresponds to the states of consciousness. Because Korea is from the IIT perspective, for example, Korea is related to the maybe or maybe not appear now. So it is possible relationship of all the possibility or some kind of linear combination of something is considered as some corresponding to the Korea. And the state is some kind of a weight of these arrows and a linear combination of arrows. So my very vague, but I believe it's fruitful that the answer of what is states of consciousness is the some states on this category.
Very interesting. May I ask a question?
Okay.
I mean, it's so one of the things that I found appealing here, and maybe it can help us think more precisely, perhaps, about the relationship between the micro level of the brain structure and the phenomenological quote-unquote macro, not really macro, is that qualitative experience usually, in particular, think about colors, for instance, which is a very famous example of sensory qualities. When I experience them, presumably there is a generative model or some generative process that makes, from my brain activity, it becomes a subjective experience. But it's obviously non-invertible. I don't see my brain through, So there is something about, it's sometimes called the problem of it's transparent. I don't see my brain. The brain is transparent, even though we have reason to believe that the level of the phenomenology has a generative process of some sort that generates the qualia. So in some sense, maybe I'm mistaken in interpreting your view, but it's non-commutative. You cannot, it's not inversible.
Okay.
Not inversible. But it's not inversible. So then there is some sort of mystery, obviously. This is sometimes called the explanatory gap. So using your framework and your thinking, how could you perhaps illuminate that very question, the generative model from the micro to the macro of the phenomenology, and the fact that it cannot be intuitively inversed because I don't, there is this idea that's the jargon that I have used in the past, that somehow the relationship between the brain as a complex set of neurons in interaction with the whole universe and of phenomenological experience is analogous to virtualization in computer science, in the sense that somehow at the level of the user interface, if as subjective agent we are like user, and the interface is the experience with which we actually interact consciously. The details of the hardware here is the brain hardware. So I wonder if that makes sense to you, and you could elaborate to that based on this structure.
Very nice. First of all, the beauty of category theory is richness of the construction. So in a group theory, you can make another group from the known group, but this construction is very restricted. in category theory, you can make another category for other category. And then now we have the another help of Rig. So actually we can construct another category from this or the state space of this. So I think the macro gap can be this is not theorem, but my conjugate, but yeah, you can construct the category of states. So from this category, you can think of another category whose objects are states and arrows the relationship of states. Actually, it is completely positive map between them. So very interestingly, you can you can assume here, we have this macro level or phenomenal level of category. So under repeating this procedure,
we have to be, I'm sorry, I speak loud just in case so that in the recording maybe, if we are lucky, you can hear it, but they can hear it. Just to point out the danger here, we don't want, I don't think, we want to reduce the problems of the relationship between the brain hardware and this phenomenological level to micro to macroscopic, because it's not like, you know, atom in a crystal where you can understand relationship spatially as microscopic crystalline structure to the actually macroscopic crystal you can observe. It's kind of it's an interesting limitation. So I think that perhaps through that kind of things we can not fall into this simplification, micro macro, but maybe think about the two.
Of course, I completely agree, and thanks for the clarification. I don't say that I'm not a reductionist, and you can start with any kind of levels, and to study the phenomenological level, you don't have to be dig into the macro level, because maybe it is just discarding our knowledge, but I'm open for the every kind of a kind of reductionism means that even if you can construct the category from here to here, it does not mean the reductionism in the narrow sense, because there is it's an equal footing as a category.
That's what I
if you are given some star algebras, the notion of idempotent, Hermite idempotent means some this kind of structure with star. This is called projection in the in general algebra. So we can think of the projection as objects. The interrelating so-called isometry, partial isometries here as arrows. Then you have the category. So this is nothing but the generalization of Grassmann manifolds. So objects are subspace. The arrows are so categorification of Grassmann manifolds. So I think this is a kind of a projective geometrical structure from this. So in the phenomenological level, we have this kind of. Okay.
I have a question on the note. So for what you take C, that is the full set, and you do the same R of C, it's in this algebra, and you know that you can see it as a constant free sheet.
So you think of to change this? Or
no, without changing. It's just here you take just ring, for example, and then you can see it as a constant.
Yes.
As a constant free sheet. So my question is, as you want to change, imagine if you want to compare qualia of different people, like have a functor from once and then C2. If you see them as sheaves,
Yeah.
you can directly look at the
Mhm,
can, you can
mhm.
look at the can extension,
Mhm.
the can, what's it called?
Yeah.
Not can extension, but it's the, so basically you just
Mhm.
look at the F and you pull it back,
Mhm.
and then
Okay,
these
okay.
are geometric morphisms.
Mhm.
So if you have enough structure, you can define. So my question is,
Mm.
could you just do exactly the same, define geometric morphisms, which allow you to go from one representation of K
I think so.
to go back?
I
Like,
think.
how difficult would it be? Like, what structure do you need on R, for example?
It's a bit. So yeah. So my understanding is that you can define another categories here, and considering a relationship between them by considering these is related. I
Yeah,
think.
so what I'm saying is that let's take it into nothing. R C, you can go.
Okay. Come here too. Mm-hmm.
So it's very stupid. I don't know.
No. Yeah, just.
You just so then you look at RC and you identify it with C going to R as a certain structure. And now if you go to C prime, you can always go from
yes.
from let's say to this.
Yes.
And then you have two adjoints, left and right, which are called can extensions.
Okay.
And the thing is, my question is, if you're inside of a rig, what kind of structure do you need to be able to do this? Why I think it can be nice is because if this is simply trying, we have two different structures and there's a communication of my case of quality as two.
Yeah.
One, the other one would like to communicate that with you.
I think the large class of rig will be okay to represent this can extension like structure. So rig. General rig for the general rig. It can be modeled this kind of structure, I think, because for example, if C is given by the simplest case, for example, in the dagger category C, this F here, the F dagger here. So here X and Y, and for X, we can make a very small category here, index. Index is category which is also monoid, but contains only the arrow from here to here, arrow to here to here, the here arrow to here to here. Then we have this kind of morphism, which becomes a CP map. So index and or then state space. This is how to say the state is as I said so we have the morphism here and also the state space here. So the pair of the CP map between algebras and states will be the role of the geometric morphism.
Okay.
So I believe.
Another question, like maybe why do you think so? How do you define states exactly? Because you didn't really say. And the second is why do you need positivity? For consciousness.
Yeah, for consciousness studies, it's very important thing. Actually, I think maybe non-positive, the positivity condition may be abundant. So if you need. So I don't have any justification for the positivity condition. Maybe the positivity condition should be abundant, but for my knowledge, there is no need to abandon this positivity. With this positivity, you can reconstruct many things because inner product should be positive in the usual Hilbert space or something. So if you have to abandon this, the theory will be very complicated. Just for mathematical technicalities, and also it is related to the quantum field theory also. You know about the indefinite metric Hilbert space. Very funny naming because Hilbert space has a positivity, but in the study of quantum field theory, there is some need for the gauge field theory. We need some negative norm or something. So, but the usual physical states should be positive in that meaning. So, negative or zero kind of norm should be erased naturally. So then the Kubo-Ojima condition is characterization of this beautiful mechanism to avoid the negativity. But it's very important. But I think that I'm open to consider the abandon positivity. For example, because some researchers in quantum foundations wants to abandon the positivity of probability. Like in the quantum physics, there is a people who use the generalized measure, like which has a negative value, negative probability or something. Maybe it works or it not. I don't know.
And can you define just maybe the states? What is the positivity condition? Because you didn't define, you said you define states?
On the generally, no.
Yeah, you didn't define the positivity.
Positivity is for C case, the general.
For the generals.
Generally. We have to define the positivity structure on the ring. The ring is this is sub-ring closed under sum and multiplication. As in the case of C, this is closed under the plus and times. And also, it is satisfies the positive cone structure. That means positive linear combination should be positive. And if the two positive things goes zero, then these are zero. By this notion, we can define the positivity structure on any link, and then. Yeah, of course.
And so then the state is positive. I mean, like this positive condition is when iota F dagger.
Okay.
Inside of our class.
Yeah. And actually, I omit, but this condition should suppose to the general notion of states on generally. In C case. This is a corollary of another. Okay. So the linear positive unital and satisfying the states.
Do we have questions from other people back in the room? If you don't have a question, I may then ask a question that might be relevant for some folks, and at least one of them is here, that are working on machine learning and reinforcement learning. A lot of the graphs you show and making analogy with neural network and mapping between different layers and different levels, it of course reminds us and probably it's very relevant but sensitivity neural network. Could you, for instance, and you talked about convolution, not in exactly in the same context than convolution and neural network, but if you had to argue in front of a machine learning specialist using neural network modeling, doing deep learning, and that kind of thing, that actually, instead of using the classical version, they should use the quote-unquote quantum. What would you argue? What would you say? And what interesting properties for machine learning it could bring? I know it's a question out of the blue, but it might be interesting.
Yeah, very interesting point.
For machine learning, to new paradigm for neural network modeling.
I believe so, because the this positive definite function is I think the machine learning researchers are familiar with these positive definite functions. And learning, so we can think of the learning on category.
Learning on
category. Because very abstractly speaking, the conventional machine learning is learning on sets. Sets means to learn the good probability distribution is the probability or some distribution is learning. So there is a good distribution. Maybe it's deterministic, but not in general, the true distribution here. Then we have the ad hoc kind of distribution and making this good and better and better. This is a very, very abstract notion of learning. But if you consider these links is very important, then the natural extension of this is the weighting of these between arrows. Then interestingly, it becomes some non-commutative aspects in machine learning. I don't know much about machine learning, but I think there is some hidden assumption that states of something should be represented by probability distribution. But in general case, there is no probability distribution. So, but state. So I think that this notions of state or positive definite functions gives you the much larger degrees of freedom to search. So for example, how to say if you know about a bromosphere or something, very intuitionally speaking, the classical bit and the qubit is the classical bit is here, and the mixture of classical probability is just here, but there is much degrees of freedom in the quantum bit qubits. So taking bit to qubits allows you the many degrees of freedom to search. So if you for example, as just an analogy, if you are stopped here, then you cannot go down. But if you can go there, you can here. So having degrees of freedom allows you to avoid the singularities or something. So I think the hidden axiom of machine learning is the state should be considered as probability distribution, classical one, that is a commutative case. But maybe the state should be more general, a linear function.
There's a very nice article recently from Borel and one of his students that defines entropy for categories in general.
Okay.
So then when this, I think it's
yeah. Entropy is very important, of course, in machine learning and more, how to say, in general setting. And I think that the construction from category to algebra to state space is related to, if you consider the category of states, then I think the work you mentioned is, yeah. Thank you very much.
So one last question from me, and I think afterward we should wrap up because it's 6 p.m. It's following up, and I'm sorry, it's sort of very, very speculative again, but as a question, I ask you to speculate. So let's take machine learning, not just the structure of the neural network, with its transfer function, its different layers, its contact structure, its connectivity structure, but also the learning algorithms that are used. One of them in deep learning, classically, in kind of feed-forward network, is the back propagation of the gradient. Would thinking, sorry, this quantum-like framework maybe help bring new ways to solve or to understand back propagation? I'm sorry, it's a very specific question. And very speculative.
Yeah, I suspect that, but not sure. But I think the more general. So usually machine learning is stratified by this kind of special. They use a special kind of category, like But I do the dagger category work. So dagger means just some structure here to here. So I think the back propagation something is this stratified version ordered sets with some other external operation, but maybe there is an intrinsic kind of back propagation like structure in the dagger category. Okay. But I'm not sure.
Yeah, speculating, it's okay. This is the place to do that. You have another question?
I think just one remark. It's really dumb remark. It's not that. I mean, like if you take a probability distribution, you look at all the projections. These are conditional expectations and sometimes that you have, and once you learn, once some instead of doing gradient descent, you can do diffusion. And then to do this, you need to have a section, and the section is the conditional expectation. But it doesn't mean that you can do it directly and that it's related, but some more probabilistic version of learning. It may be more.
Especially at least in the quantum cognition studies, it strongly suggests that our learning, not machine learning, obeys more non-commutative property. So I don't know it's good or not, but if you want to mimic our learning, then maybe this kind of categorical structure is useful, I think.
Okay, I just queried one person that is still online to see if that person wants to ask a question. So we'll see, but maybe not. But as we wait in any way anticipating, I really appreciated your talk. Christophe van der Margoed, he had to leave, not stay for the entire discussion, but he said very interesting talk, accessible, my head is swirling. I will look into this paper, I will leave now, as I cannot follow well the discussion. Yeah, there is a lot to think about. And obviously, it seems that, at least I'm convinced of that, we all have to get better at math, and we are lucky to work with good mathematicians if we want to solve or approach the solving of the problem we are trying to tackle. Anyway, thank you very much.
Thank you very much.
I'm
very
nice,
happy to hear that. Thank you.
And see you all next time. I'm going